Hello, in this video we're going to continue with Lab 2 and we're going to go over the multi-stage op-amp. So in the directions it says that we're going to design and simulate a 3-stage transistor level BJT op-amp. It's going to have a differential input stage with large input resistance, a gain stage, and an output stage with low output resistance. Per the requirements, it's going to be comprised of small signal BJT transistors as well as resistors and capacitors. This part is important. Try to minimize your component count. So when you're coming up with the design that you want to do, keep in mind to try to keep it simple, but at the same time improve your circuit characteristics through design iteration. So that means, looking at chapter 4 and 5 and looking at the different current mirrors, and does the circuit have an active load, and then also like the output stage, how can you get lower output resistance from the amplifier? So an example of a 3-stage BJT op-amp is provided in figure 3.2. And so it says if you have a choice to use the same or different configuration, if you choose to go with the same example, you will need to do a bit of research on your own. This is only fair since you will be saving the time to select and design the individual stages from scratch, and will also make the lab a more enriching experience. So looking at the provided schematic, we see the differential input, we see a current mirror, this is going to be your gain stage, and this is your output stage. And so the second stage consists of a PNP type cis-Cli pair. And so that is this configuration right here. It's also known as a compound Darlington. And the third stage, which is the output stage, is a simple push-pull output. So this is a Class B push-pull. We can tell it's a Class B because it is conducting for 180 degrees of the signal life cycle. So one transistor turns on during the upswing, the other transistor turns on during the downswing. So when you're thinking about what design you want to go with, I would first look at a few op-amp data sheets. So I've got a few pulled up, and in the data sheet there's going to be a functional block diagram, which is the operational amplifier as if it was made out of transistors. So it's kind of like the schematic of the op-amp. So this is the LM741, and you can see that it's made out of BJTs. And I know there's a lot going on in here, but it's a good idea to just kind of look at sections and see what you're familiar with. I can see the differential input. This is obviously the offset null, but it looks like a current mirror to me, possibly an adjustable one. Another current mirror up here. This looks like a active load, possibly. I see a Darlington array, and then we have a push-pull configuration, and I'm seeing this NPN and this PNP. So there's a lot going on. I would not recommend trying to build this for this lab, but it's good to just look at some of these different op-amps. So this is the LM358, and this is their block diagram. You'll notice they have their differential input. They use an additional additional transistor to increase the input resistance. We have the current mirror. They have, looks like a gain stage. And here's another Darlington array that goes into their output stage. So it's a NPN Darlington that goes into a PNP as their output push-pull. This, I would still say, is a little bit too much, you know, and like I said, I would just keep it simple. And let's look at another one. So this one is a LM386, which is a low voltage audio power amplifier, and we can see it has the differential input with the extra transistor to increase the input resistance. There's the current mirror. We have a gain stage, and we have the output stage. So this is a constant current source, which this is an active component. So per the lab manual, it's supposed to just be transistors, resistors, and capacitors. You could swap that out for a resistor. And then I want you to notice this configuration. This is that same PNP cis-Cli pair or compound Darlington. And I will go back to the lab manual, and you could see it's identical. So I went ahead and made the LM386 in LTspice. And I wanted to point out a couple things. So if you were to run this, and we're sending a 200 millivolt peak-to-peak signal in, and you just take the output, we're writing a DC voltage. Okay, so let's go back to the data sheet. And we're going to go to some of their suggested configurations. So here's their first application, and it is a configuration with a gain of 20. So we can see you're sending the input into the non-inverting pin, you're grounding the inverting pin, and then you're just taking the output. And then there is a filter here, and you add a capacitor to the output, and then a speaker is usually around 8 ohms. So we know that the load impedance is going to be rather low. So let's go ahead and add those additional components and see if we can get that DC offset to come down. So I'm going to make this 470 microfarads, 47 nanofarads, and 10 ohms. And let's do it without a load to see if we get what we want. And you can see I changed the constant current source, and I'm using a 5K resistor. So now we got rid of the offset. Okay, so we're sending in 200 millivolts peak to peak, and we're getting 4 volts peak to peak. So we're getting a gain of 20, which is exactly what it said on the data sheet, but in the lab manual, we need to get a gain of 10. So looking at the data sheet of the LM386, let's go down and look at another application. So this other application gives you a gain of 200. So we are at 20, and to get a gain of 200, you connect a capacitor between pins 1 and 8. So now I'm going to go into my LTspice model. I put texts to show pins 1 and 8. And so you would add a capacitor in here, which is shorting the AC signal. So to decrease the gain, we would need to add resistance to R2. So if we roughly double that and make it 3K and then run it, now we're getting a gain of 10. Okay, so the point of this lab isn't necessarily like if you were to take my model of the LM386, you would still need to write in your report why there's 2 transistors here. You know, specifically show with some of the formulas how does it increase the input resistance. And you still would need to research the PNP cis-Cli pair. So those are a couple, this is just another option, right? This modified LM386. So talking about the PNP cis-Cli pair, I wanted to show you a resource that helped me. So there's a website called Elliott Sound Products, and I've been getting into them a lot lately because they have tons of stuff. And in the search bar, let's just put cis-Cli and see how many. So this is how many articles they have that term cis-Cli pair in them. And the first one is compound versus Darlington. So this article is going to go over the difference between a Darlington and a compound pair. And if you look, this is the PNP cis-Cli pair, and it might look a little different than the one in our schematic, but you can see it's because in our schematic the emitter is on top and the collector is on the bottom. So it's just flipped over. So I highly recommend reading this and taking a few key takeaways and putting it in your lab report in the PowerPoint. And I think one takeaway that I got when I was in the course was these output stages. And I'll get back to the output stage in a second. But I wanted to point out that you see this is exactly the same as the schematic from our lab manual, right? We have a 1K RE resistor, we have the capacitor, compensating capacitor, and we have some resistance between the base and the emitter of the NPN. And that's exactly what's going on here. So go ahead and read through this, try to get some key takeaways, and I'll get back to the output stage because that's what I wanted to talk about next. So in the lab manual, we have this output stage. That's a Class B amplifier. And so I got this model that I made. A Class B amplifier takes the signal in. As it goes up into the positive voltage, it's going to turn on this transistor once it reaches over 0.7 volts. And we'll see that on the output. And then once it swings low and goes down into the negative portion of the cycle, it's going to turn this transistor off and it's going to turn this one on. and then you will see that on the output. So both transistors are switching on and off for 50% of the cycle. And so if we run this, here's the input, and then the output, we see this crossover distortion. And so that crossover distortion is the time that it takes to reach that threshold voltage. If you think about it, we're missing about 1.4 volts of this signal. So I'm not going to show you how to do it, but I would recommend looking up Class AB amplifiers. And what that is you're just adding 0.7 volts DC on the base of each transistor so that the input voltage is seen at the output without having to reach that threshold voltage. Okay, so Class AB amplifiers, check it out. And then going back to the compound Darlington pair, this is a push-pull amplifier, right? You have your PNP cis-Cli pair down here, and you have your NPN cis-Cli pair. And you can see there's these diodes that help bias that base to allow it to get rid of that crossover distortion. So just some things to check out. I hope this helps, and we'll see you on the next video.